So yeah, thanks for that. Yeah, as Lily mentioned, I work for the British Geological Survey. I've been there quite a few years now. I did my degree at Bristol, followed by a PhD in sort of geomorphology and landscape evolution, and then I joined BGS in 1996. And I was put to mapping in Southeast England, and I thought, oh God, this is a bit tedious. I'd rather be mapping somewhere exciting like West Wales or in Scotland. But actually, it turns out that yeah, Southeast England is actually quite geologically interesting and in some ways challenging. So what I'm going to talk to you tonight about is about some of the work we've been doing in the last sort of 5 or 10 years in Southeast England. So I'll just start to share my screen. So it should be on slide view now. So applied geological mapping in Southeast England. So we've been working quite closely with both the Environment Agency and the water industry over the last few years. I noticed Nigel Hode's in the audience, so it's partly down to him. Working to produce and to update some of our geological maps across southern England. Not just southern England, but also going up into the Yorkshire Wolds as well. Main driver behind this is actually the increasing pressures on the chalk aquifer. So not just looking at groundwater quality, but also the groundwater as a resource. It's also partly been driven by the fact that for many years chalk was just mapped, and they just assumed it was kind of lower, middle, upper chalk. That was all done. That's all you needed to know. But it's also quite clear that from the work that Rory Mortimer has been doing since the mid '80s, that actually the chalk is a lot more diverse and complex than just lower, middle, upper chalk, and it's actually quite important from an engineering and infrastructure point of view. So that's kind of why we're kind of been focusing on the chalk for quite a lot, since I joined BGS actually. So where are we working at the moment? We've been doing a series of catchment scale projects in the Chiltern Hills. Again, working with both water companies and the EA, so that's Thames Water and Affinity. But also in previous times, we've been working with Southern Water on the South Downs as well. So we're currently working. We've been working in the various catchments across the Chilterns, so the Misbourne, the Chess, the Gade, up into the Bean. We've done a bit of work in the Upper Cam for Affinity Water. And we're currently working on 2 catchments. One is the Ribash Stort up towards the northeast, and also down in the Henley area at the moment. And in fact, I'm actually currently based in Marlow because I've been at the field this week up until about an hour ago. So working in that area. So actually, it's mostly on the chalk, but we're not just mapping the chalk, we're also mapping the superficial deposits, but also down to the lower green sand, actually the upper green sand, and also partly on the Paleogene. And in the northeast, we're also working on the extensive glaciogelic deposits, the Anglian glacial tills and the extensive fluvial glacial and Paleothermal terraces. So I say it's not just chalk; it's actually quite a diverse geology across the region. So why are we studying the chalk? Well, I mentioned it's about groundwater. Well, clearly, as I suspect most of you in Southern England know, that a lot of your groundwater comes from the chalk, supplies an awful lot of people. But also there's growing demand for water, but also issues with water stress, low flow streams, that kind of stuff, and also the impacts of a changing climate. So you can't just pump water from the aquifer without actually thinking about where it's coming from and how much water there is, and what's going to happen to groundwater levels and streams if you just carry on pumping. There are also issues with contaminants, particularly nitrate, pesticides, and a whole series of novel contaminants as well coming through, which means, again, you've got to know where your water is coming from. So if you've got a particular borehole that's got a contaminant in it, you need to know where, start thinking about where the water's coming from, in order to address that issue. And that requires understanding a bit more about the geology. So that's why we're working with the EA and various water companies. And of course, there are also various pressure groups as well, like the River Chest Association, for example, and quite often makes the headlines about contamination with sewage and that kind of thing. But as I briefly mentioned at the start, it's also important from a civil engineering point of view. If you think about the amount of major infrastructure schemes that are actually in the chalk, and to some extent in the lower part of the Paleogene sequence, you've got things like the Lower Thames Crossing, Stonehenge Tunnel, HS2, Crossrail, the London sewers, various pipelines going across the region. All those are going to impact on the chalk, and in these days, you often actually need to know more about the geology before you start construction than you did in the past. So, for example, a tunnel boring machine, you actually need to know what you're going to go through, because in order to design the cutting heads, for example. So if you're going to go through a bit of the chalk with a large number of flints in it, you need to design a different cutting head to one that you're going to do if you're going to, say, go through the lower chalk sequence. And it's also not just about the chalk itself, but also how it weathers, the periglacial weathering of chalk, and how that influences the engineering behaviour. And as probably many of you may now be aware, the chalk is not just a simple, uniform, white flinty stuff. It's actually got quite a lot of heterogeneity within it, both within and between different formations. And the lithology actually also influences the fracture style. So, in certain parts of the sequence, you get conjugate fractures, particularly where you've got thin marl seams. In other parts of the sequence, you tend to get vertical fractures. And that has a big influence, particularly on, for example, cliff stability, but also on the type of failures you might get in road cuttings or in tunnels. So if you've got lots of conjugate fractures, you might get wedge failures in a tunnel, whereas if you've got vertical fractures, you're going to get toppling failures, but that kind of stuff. There's also significant variations in the flint density and style. So if you're drilling a borehole through or a tunnel through parts of the seafloor chalk, you're going to know about the flints, and whereas if you're in the lower chalks, then flints aren't a problem. But the flint density and style also varies spatially as well. So you find there's a lot less flints, for example, in East Kent, but if you come further southwest, then you get a lot more flints. I mentioned periglacial weathering, the formation of destructures and putty chalk. That's particularly important in East Anglia. There's also the role of karst with sinkholes, irregular rockhead, and various other issues to do with the dissolution of the chalk. And what we have noticed in the last 10 years is a lot more stream sinks and karst features than have been previously recognised. And of course, we've got a history of natural sinkholes, but possibly more importantly in southeast England, anthropogenic collapses like over old chalk mines and dean holes and the like. And of course, quite a few of these make the headlines. For example, back in 2014, I think it was, or 2012, when we had a big spate of them. So, one of the things I often get asked by people when I'm, so I mentioned mapping the chalk. Well, people go, haven't you done it already? Well, we did, but often quite a long time ago. And of course, the rocks don't change, but what we know about them does, and the amount of data that we have also improves as well. So, clearly we've got increased stratigraphical resolution, particularly with the chalk group, but also the Lambeth group as well in the Paleogene. We've got much better understanding of the Quaternary and how the climate has changed over the Quaternary time scales, but also how that impacts on the engineering properties. We've got lots of new data sets, not least the new EA LiDAR, which has really revolutionized how we can map, and some of the features you can identify, old pits and shafts and stream sinks and stuff. We've got a lot more geophysical data, downhole logs, but also spatial geophysical data, and of course a lot more boreholes as well. So all those things are going to help us improve the maps. We also can map in different ways. We've got 3D modeling software now, much more readily available. We've got better geophysical techniques. We can do laser scanning, all that kind of stuff. So there are different ways of working and different ways of acquiring and interpreting data. And of course, the other thing that changed over the last sort of 10, 15 years is that what we can produce. It used to be that we just used to produce a geological map and a memoir, and that was it. But actually now we can produce lots of different data sets and products from those geological maps. For example, hazard maps and 3D modelers and visualizations of things. So much more tailored to what the end user wants. And that's also partly been driven by a change in user requirements. And in the old days, people just wanted a paper map and that was it. Well, people still want a paper map, which is great. But also, there's much more. There's been a much bigger shift from people wanting 2D information to 3D information. And particularly now, we've got ways of both generating a 3D model, but also showing outputs from the 3D model and how people can visualize that on their either on their computers or through virtual reality or whatever. And then the final thing is that actually, in some cases, it's the geological data that starts becoming a limiting factor. So when you start doing groundwater modeling, for example, at the moment, the groundwater models can only take a certain amount of geology, real-world geology, but actually as time goes on, groundwater models become more sophisticated, better computing. It's the quality of the geological data that starts becoming limiting things. So chalk strat. So some of you may be familiar with this stuff, some may not, but the chalk used to be mapped into just lower, middle, and upper based on two hard marker beds, the Melbourne rock at the base of the middle chalk and the chalk rock at the base of the upper chalk, both of which are quite prominent in the Chilterns. But as you move way down to the further south and up into the north, the chalk rock, for example, is diachronous and dies out to the south, and you can't actually recognize it. So on the Brighton sheet, it was mapped as lower chalk and then middle and upper chalk undivided, which is actually not much use to anyone really, particularly the engineers. So we now divide the chalk into about 9 different units, depending where you are, because part of it's been cut out by the page nonconformity. So down on the Isle of Wight, you've got the full sequence up into the Portsdown, but around where I'm working at the moment in the Marlow area in High Wycombe, you've got basically the paleogene cuts out to about the middle part of the Seaford chalk. When you go further north across the Wash, the chalk changes, and you're getting different stratigraphy. Basically, the fasces changes. Nice thing about the Southern Province chalk is that you can trace this right across the basin, right across into to northern France. It's not just the individual formations as well, but there's also individual marker beds that can be traced as well and identified. And the other important thing is that this is very much an engineering based stratigraphy. So, and of course, it's the engineering properties that affect how the chalk weathers, and therefore how that also is reflected in the landscape. So you can trace this through because they're reflected in the landscape as different breaks of slope, that kind of thing. So they are mappable units. You can't. It's not just a case of seeing them on the coast, but you can actually trace them inland. So when you start looking in more detail, you've got the various formations, but also within each formation, you've got lots of discontinuities. And these are mostly hard grounds, marl seams, and flints. Hard grounds are basically the periods of non-deposition and hiatus, where you're getting a sedimentary hard ground forming on the seafloor. It's basically much harder chalk. The most well-known one is the chalk rock, but other ones also occur in various places. Marl seams, these are thin, very thin beds of clay, usually just a few centimeters thick, rarely more than rarely more than 10 centimeters thick. But again, these reflect naturally extensive stratigraphical features that can be identified right across the basin. And so here's a photograph of one, and they also influence groundwater flow as well, quite significant in the development of karstic conduits and causing natural discontinuities in groundwater flow. Likewise, the semi-tabular flints. Some of the bigger flints, particularly the Seven Sisters flint in the lower part of the Seaford chalk, you can trace this right away from East Yorkshire, where it's known as a different name, all the way down through the Chilterns down into southern England and right across Dieppe, in fact, right across the other side of Paris. And you can see here, I put in the Normandy stratigraphy, there's certain key marker beds that can be traced right the way through. But equally, as you come up, at the edge of the basin, you get different formations, different stratigraphic units coming in and different discontinuities. So as you get towards, for example, Rouen and Le Havre, then you start getting a lot more hard grounds coming in, for example, as you're near the edge of the basin. So a lot of these named flint bands, marl seams, and hard grounds are very useful stratigraphic markers that can be traced right across the basin. So here's a image of Seven Sisters at Cuckmere Haven on the south coast near Eastbourne. This is one of Rory's images. And again, you can see that you can trace these individual flint bands all the way through. And you can also start to see here that this is the middle Seaford chalk here, the Haven brow beds and the Cuckmere beds. And here you've got very, very strong vertical fractures. But in the lower beds where you're getting some marl seams coming in, you start beginning to get some conjugate fractures coming in, and that has a big impact on the cliff morphology. Now, as I mentioned, you can trace some of these beds right across through to Yorkshire and down to Paris. And of course, this is very important from an engineering point of view, because it helps you in different ways. Could it help you obviously identify the engineering properties of each individual unit you're going through? So you can recognise those marker beds within your boreholes and sections, and you can identify what you like to encounter. But also, it helps identify potential faults. So, if you just go call all your unit upper chalk, you can't see you can't distinguish between the different parts of it. You can't then identify where there are any faults. So mapping out these individual formations and in some cases the marker beds and the members can help you identify the structure and in particular faults. So just today, in fact, I'll just identify some faulting based on tracing out some of these marker beds. So that's quite key for identifying and designing the engineering ground models for various big infrastructure projects. So this section here is part of the High Speed 1 Thames tunnel. But you can see they identified small fault in the cross section, and likewise we've done similar work for the Lower Thames crossing, whereby we can identify where you'd like to find areas of poor ground quality due to faulting, for example. Similarly, in the Stonehenge tunnel, they also identified some phosphatic chalk horizons, which have caused some significant engineering headaches, which of course have a big impact on the cost of Stonehenge of the tunnel. So coming back to the Chilterns, so this is the published map of the Aylesbury area, the Aylesbury sheet. So this was last mapped in 1912. So clearly, in the intervening period, we've now revised the sheet. But clearly, what they mapped in 1912 was fine then. But obviously, with the changes in the quality of the data available and our understanding of the geology, we can now do a much better job. But until relatively recently, this is all information that people had on the geology of the area. Of course, HS2 goes through part of this. Likewise, the Hertford sheet is another one where it was very much based on old data. Again, we've largely revised this one now as well. So this will be going out in the next version of the digital geological map. And the reason why the mapping is important is because, of course, it is the baseline data, the raw geological data. And I do kind of envisage like a Jenga pyramid. If you get the mapping wrong, then your 3D models are incorrect, your derived products are incorrect, your ground models for engineering purposes are incorrect. So it's you've got to get the maps, the mapping right in the first place, or at least make it as good as you can anyway. So that's why it's worth spending a bit of time doing the mapping. And there are also some other issues as well that stem from the antiquity of the existing data. In many cases, the old maps are not so much, they're not incorrect in the geological sense, but they're incorrect in a topographical sense. This is an example from the Chilterns, where you've got the chalk rock, which is this darker green band here. And if you look at the map, it looks like it goes up and down the contours quite significantly. It looks like it's quite significantly folded. Well, this is actually an artifact of how when they mapped it, they only had a topographical base map, probably with 100-foot contours, if that. So they knew what they were mapping in a geological sense, and they were plotted it on their map. But of course, when you've only got 100-foot contours and you haven't got GPS and you haven't got DTMs and the rest of it, and you haven't got the modern topographical maps, they weren't able to plot it out particularly accurately or very precisely. And therefore, when you drop that existing line back onto a modern topographic map, it no longer fits. So so that kind of makes it hard to identify whereabouts exactly is the chalk rock going to be. Is it going to be up at sort of 175 meters OD, or is it going to be down at 155 meters OD? So this is why I say that because of the changes in the quality of the data available, you can actually do a much better job. Likewise, this is another example from the Upper Cam Valley. So this is the M11 coming up. You can tell the M11 by all the boreholes. And then on the sheet to the south, this is the Epping sheet, I think. We've got a buried valley here mapped, and then you come up to the edge of the sheet boundary, and this is a much older map. The buried valley basically wasn't recognised. They didn't have the borehole data, they didn't have the geophysics. But more recent boreholes in this area here, which is mapped as chalk surface, boreholes actually prove a significant depth of superficial deposits. There would have been a thin skim of superficial deposits across the whole area, so it would be quite hard to see the chalk at surface. But yeah, there's a lot. Just go show that with more data, you can improve the maps. So that's kind of the chalky stuff. We've also been looking at the superficials. Clearly, since the area's last map, there's been a huge revolution in our understanding of the Quaternary deposits, not least all the Paleo-Thames terraces, which some of you may know. The Thames used to flow from its present course around Reading and then flow north-east through the Vale of St Albans and out across East Anglia, depositing a whole series of Thames terraces, the Western Green and Beaconsfield and Giles Cross terraces, all the way across through this region. And on the old maps, it's just shown as plateau gravel or valley gravel, because it didn't have the topographical and conceptual understanding of the deposits to actually improve on it. Because we now do, and we can actually map out all these individual terraces right across the region. And I'll show that some of that in a minute. So how do we actually go out doing the mapping? You know, most geologists have got experience of doing their undergraduate field mapping in places like Arran or Skye or whatever, where you've got lots of rock exposed at the surface and it's relatively straightforward. Of course, across much of South East England, you don't actually see much of the rock because it's either covered in vegetation or soil or whatever. But there are still plenty of clues in the landscape. You've got evidence from old pits and quarries where you can actually see the rock. A lot of these are degraded now, but you can still see enough. It's amazing what you can find in rabbit burrows and badger scrapes. You know, all you need is maybe a few fossils and that will tie things down for you. You've got breaks of slope. So I mentioned that we can use changes in the break in slope to help map out some of the features. We can use vegetation. You can see on this image here, you've got some gorse on the top, which indicates quite an acidic soil. So there's probably a bit of clay and flint rather than chalk on the top. We can use changes in what's been brought up in the plough. So here it's quite visible on where you've got the chalky soils versus a more sandy soil. So that kind of thing. So there's lots of clues in the landscape. But often you've got to get in and look for stuff, you know, look for clues in old pits, for example, which are usually now very much degraded. So you have actually got to go and scrabble around a bit. We also use fossils. So as you go through the chalk sequence, you've got different fossils at different horizons. And some are actually very, very useful, some less so. So, for example, if you're up in the New Haven chalk, which you see around in parts of, particularly in southern Hampshire and the Isle of Wight, but also up into parts of Kent and up into the Yorkshire Wolds, Marsupites only occurs in about a 20-metre interval of chalk. So if you find Marsupites, you know where you are. Likewise, Volvoceramus associated with Platyceramus is very common around the level of the Seven Sisters Flint. And it weathers out really nicely, so you often find it in the field, in the plough or on rabbit burrows, that kind of stuff. So that's a very useful marker bed. So we use the incoming of Platyceramus and Volvoceramus to help map out the base of the seafloor chalk across the Chilterns. And micrusters are often used in the past. They're great. The only trouble is that they're not often well preserved in the field other outside pits. So you don't often come across them in ploughed fields, whereas the ionocerama bivalves you do. So a lot of the early work was done on basis of micrusters, but actually the ionocerama bivalves are far more important for us. In the lower part of the sequence, you get various ammonites as well. Acanthus rotemagensii, Acanthus jux browni, for example, down in the zigzag. Again, other types of ionocerama bivalves. So we do still use fossils quite a lot. We have also used air photographs, which of course weren't available to any of the field geologists before the Second World War, really. And that's a great help when coming to map the superficials. And you can often distinguish various head deposits, patches of till. In this case here, this is up in near South Audron, northern Chilterns. This image to the right is down near just north of Hertford, and you can see that the gravels, some of the outwash gravels in the valleys, come out as pale on the air photographs, but the till, being more clay rich, comes out as a much darker colour. So you can see also some of the valley bottom heads here as well. So straight away you can almost draw your boundary, bam, straight through. So it's very useful. We also use EA LiDAR, which is again fantastic, and it's brilliant for identifying things such as old chalk pits. So you can straight away know that, oh, okay, there's a chalk pit there, but I'm going to have to take a look. But you also identify gravel pits, which tend to be much shallower and more extensive. So this is an area just north of Slough in the Burnham Beaches National Nature Reserve. So this is where we're working at the moment. You can identify stream sinks. You can see the stream coming down here and then disappearing just in here. And likewise, you've got a stream coming down here and disappears just in here and coming down there. There's another one there, in fact, and one down here. So again, it gives you targets to go look for. Lots of sinkholes. These conical depressions are large Sophosian sinkholes in the Paleogene overlying the chalk. And also, you can see here there's actually a landslide as well. So where the clay-rich Lambeth group is actually slumping down into the sinkhole. And the LiDAR has actually been brilliant because you can actually identify a lot more landslides across the UK now than our maps show. So there's a deal of work now to do to go through some of the LiDAR data and actually update our maps based on that new data. This is another example again from the Marlow area. This is River Thames. Henley is just down off to the left. It's River Thames going down through there, but you can see some chalk pits, some gravel pits, but you can also pick out the edge of the alluvium. So you can start picking out some of the river terraces, and for example, breaks of, major breaks of slope, for example, like here. So, so again, using the LiDAR data and colouring it up can help you identify all the various terraces. And on a more regional scale, you can use DTMs to kind of identify gross features in landscape and things like that. So here's a view looking across the Chilterns. So in the southeast, in the bottom corner here, you've got the Goring Gap, the River Thames coming through past Wallingford, through Reading, around Henley on Thames, Marlow's just here, through Maidenhead and Slough, and then off down through London. So this is your main Chilterns Cuesta, the escarpment through here, the dip slope. But you see there's a big change when you get to this area here. The scarp is much more subdued. You've got a couple of big gaps here. And this is where the angular ice sheets come down and basically bulldoze the chalk scarp. So, so this is the edge of the angular ice sheet coming through like that. And it has a big impact on the landscape. And again, you can see where the River Thames used to flow through. It's not always out over this way. It now flows to the south. So this kind of visualization really does help you understand what's going on. And this is what the old geologists back in when they mapped, back in the 1920s, 1910, just didn't have. We also have geophysical logs. So we use these quite a lot. My colleague Mark Woods does a lot of work interpreting some of the geophysical logs from the water companies and EA boreholes. And these are brilliant because they give you a really good handle on the thickness of the units and how they vary across the area. So you use basically inflections in the resistivity and the gamma logs to identify certain marker horizons. So things like the Plins Mars, for example, at the base of what used to be called the middle chalk, base of Hollywell chalk now, is a really good kick on the resistivity and gamma logs. You can correlate those between all the boreholes. You can start to bring up really quite nice correlation panels, so you can actually look at where the chalk units may be thick or thin, or whether there's some anomalous things going on, including potentially faulting as well. So that's been a real godsend over the last few years to look at some of those geophysical logs. And they're extremely useful when you're coming to do 3D geological modeling. The other thing we've been using very recently is passive seismic methods. This is quite a new technique, using a device called a Tremino, and it's basically a seismometer, but it just measures the background passive seismic noise in the Earth's crust to create essentially a seismic cross section, using shallow subsurface. And we've been using it a lot recently, particularly in the east of the Chilterns, to help identify and characterize some of the buried valleys. Because of course the buried valleys, usually you recognize through borehole logs, and of course boreholes are usually quite sparsely, quite sparse in their nature. They're not particularly well. They don't often have a good spread of them, and often you might just have one borehole proving 30 meters of glacial chill, and then that chalk's outcropping nearby, but you don't know exactly the depth and the geometry of these buried valleys. So we've been using these passive seismic techniques, and you do like a traverse across some of these buried valleys. So this is the Bean catchment. This is River Bean coming down here. Stevenage and Hitchin Gap in the northeast there, and there's a big buried valley coming down through the Stevenage Gap down towards Hertford. So I've done various cross sections across some of these buried valleys, and you can see that it was quite good. You can get quite good constraints on the geometry of some of these things. The depths are always slightly more difficult to interpret because you've got to have you understand the seismic velocities a bit better, but it certainly gives you an indication of where these things are. And we also use it to try and get an estimate. So maybe some of the thickness of the glacial till deposits on the interfleets, for example. But the other thing we can also use it for is to identify faults. So we've used it in the Yorkshire Wolds to identify faults in the subsurface. And we've also done similar work in the Cotswolds. Because what you often see is you might have a good reflector, horizontal reflector coming across, and then there'll be a zone of vertical discontinuities, and then the reflector carries on at a slightly different level. So how does this pan out? Well, as an example from the River Tess and the Misbourne in the Chilterns. So to put you into context, this is the River Thames down here. So Marlow is in here, High Wycombe is in the middle of it there, and this is the Misbourne coming down here. So HS2 is coming through there. This is the Chess catchment. The M25 comes around that bottom corner, bottom left hand, right hand corner. So this is the old map. So basically, this is the existing data in dig maps. This is the Aylesbury sheet in the top corner. So basically upper, middle, and lower chalk. Just 3 units shown. This is the Beaconsfield sheet, which was updated using a dust study from existing data, where they're able to put out the Seaford chalk based on some of the old field notes, mainly relying on paleontology. Again, we've improved that. And likewise, this is the Henley sheet over here, which is again just lower, middle, upper. You can see the various edge match issues. But when we do the new mapping, you can see there's quite a radical change in our depiction of the geology. And in particular, we've identified some quite significant faulting in parts of the region using this new chalk strat. In part helped actually by some of the HS2 boreholes coming through here. This fault here, you can actually trace through right down towards Marlow, coming right down here. In fact, that's just the areas we're working in today. And likewise, you've got some more faults coming down through parallel the M40 from Stoke Church all the way down through down to Lane End and High Wycombe. So, yes, significant improvements to the map. Likewise, we can make significant improvements to the superficial geology as well. So we've got these, as I mentioned before, we've got these staircase of river terraces. Some are pre-Anglian, so dating to before the River Thames was diverted. We've got the Anglian glaciation coming in, and then post-diversion Thames terraces in the lower part of the sequence. And again, we can identify these in the field from boreholes, from field mapping, but also from sections, both old worked out pits, but some of the active more recent pits as well. And then we use that information and you can start to piece it all together in a 3D model. You can start to look at where you've got this is a cross section through part of the region. You've got some of the pre-Anglian Thames terraces, terrace 2, 3, and 4, or 1, 2, 3, and 4. Ice sheet comes in, overrides it, dumps a till on top. Then you get a feed of that wash channel cutting down into the till, removing some of it, and then you get your post-glacial river terraces and alluvium on top. So you can get quite a complicated sequence, particularly through the various St Albans. And that has a big impact on groundwater flow, for example. So if you might have water coming off the Paleogene, sinking into the chalk, and then coming to a borehole down here. But you might find that the heads you get in the borehole coming down here are actually very different from the head you get in a borehole that just goes down into the Anglian Till, for example. So, so it does have a big impact on the hydrogeology. So this is an example from the Vare catchment. So this is the old map. You have basically the brown stuff is your clay or flint. Your blue here is your glacial till, and then this was just mapped as glacial gravel down here around St Albans. But actually, when we remapped it, you can for a start, there's a lot more superficial deposits than was previously mapped. There's a lot more periglacial slip deposits, fluxion deposits. But equally, there's a lot more. We can identify the different River Thames terraces. This is a bit further to the southwest. You've got this is M25 coming around. So the M1 coming up through here, the M25 coming around and through here. So this is around Watford, Radlett. You can see the clay or flint. These coloured bits here, the individual Thames terraces. And you've got one set going like that, the other set going like that. Then you've got the Anglian till coming down from the northeast, blocking off the River Thames and causing it diverting it southwards. And then you've got the post-glacial River Colne terraces coming in later on. So there's quite a complex story that has been unravelled partly from people looking at the gravel pits, people like Phil Gebhard and others working in some of the gravel pits and looking at all that kind of stuff. But we can now map it out properly. I mentioned Barry valleys. These have a big impact on groundwater flow. So obviously, if you've got your chalk aquifer and then suddenly there's a great big 30-metre deep wedge of glacial till cutting through it, and that's going to have a big impact on your groundwater flow. And of course, a lot of these are not very well characterised on our published geological maps because back in the day people just didn't realise they were there because you didn't have the borehole data. But nowadays, of course, we can do a lot more. We've got the geophysics, we've got more boreholes, we've got a lot more potential data we can look at. So when we're working in the Stevenage area, we can actually identify a lot more of the Barry valleys and actually get some understanding of how deep they are and how they vary along their profile. So, for example, the Stevenage channel is really quite deep at the top end, but it gets quite much shallower down to the bottom. In fact, by the time you get down to towards Hertford, then in fact it's no longer a buried channel. It's actually just a series of terraces preserved on the valley side because the bottom of the buried channel is actually now above the river level. The river's cut down through it into the underlying chalk. Likewise, this buried channel coming through the River Bean is quite interesting because that has a quite big impact on groundwater flow. So in the northern part of the Bean catchment, you've got your typical headwater chalk stream coming down, often dry in the summer months, just as ephemeral streams. You get to where the Barry Valley cuts through across the valley, the present river valley. And it basically acts as a groundwater dam. You've got upwards of 30 or 40 meters of glacial till cutting through the chalk, acts as like a groundwater dam, and you get springs just above. You get a perennial stream flowing past across the Barry Valley, and then a little bit further south, the current river valley goes back onto the chalk, crosses over the Barry Valley, goes back onto chalk, and then sinks. And in fact, the lower part of the Bean Valley is often dry, even when it's flowing to the north. So basically, water comes through the chalk, meets the Barry Valley, comes out at the spring, flows on the surface for a bit, and then sinks before coming out at the springs further south. So clearly, these Barry Valleys are quite important from a groundwater perspective. So once we have all these new maps and all this new data, and we can then start to think about doing stuff in 3D, creating a series of 3D models, because actually that's what a lot of people actually want these days. And there's various ways you can do groundwater geological modeling. You can do it implicitly or explicitly. So we tend to use either GoCAD, which is particularly useful where you've got a good quality borehole or seismic data, or if your borehole data is not so good or you haven't got much good seismic, then we tend to use Groundhog. And Groundhog is much more manually driven in the sense that it uses the geological data that you've collected and interpreted to create your model. You can't. Some models you just basically put in all your borehole data, put your seismic data in, and press a button, and it creates a model. Other methods you tend to be far more manually driven, so you have to draw cross sections and create a model that way. So the type of modeling we do depends on the type of quality of the data we've got, and also on the size of the model, and how deep the model is going as well. So in the Chilterns, we tend to use groundhog because the quality of the borehole data is not very good. A lot of the boreholes just say chalk, which is not terribly useful. The engineering boreholes for construction schemes are usually much better, but they're often quite shallow and obviously just along a single routeway. We've got a lot of boreholes dating from the Industrial Minerals Assessment Unit that was done back in the 70s and 80s at BGS, looking for industrial minerals, mostly gravels. These are very good for looking at the gravel deposits and terraces, although they're sometimes misinterpreted. But of course, they don't tell you anything about the chalk. So the borehole data is a bit of a mixed bag. So when you try and do a catchment scale model, you've actually got to rely heavily on the existing map data, on the new map data, rather than boreholes. Likewise, the passive seismic is great, but again, it relies on knowing the seismic velocity. So getting the depth control is quite difficult. And ideally, needs to be tied up with borehole control. But we'll say anyone who does the modelling really does need to understand the geology, because that's quite key. So what we've been doing a lot of, particularly in where you've got a lot of the Anglian glacial deposits, is create a series of cross sections. So these blue lines illustrate some of the major cross sections that linking some of the key boreholes. You can see that where we've got the Barry Valley coming through the Stevenage Gap down towards Hertford. We've done a lot more cross sections based on either where we've got some boreholes or where we've done passive seismic cross sections to try and help constrain the model. And this is the kind of thing we can get out. So both looking at the bedrock. So the panel on the left here is a Seaford chalk. So we can start to pick out both the outcrop, but also the thickness of the Seaford chalk beneath the interflues. And then likewise, the map on the right is the thickness of the Lowestoft till, the Anglian glacial till. You can see in places on the interflues it can be 20, potentially up to 30 meters thick in places. And then in here we've got a bit of a Barry Valley where you've got a couple of boreholes, which suggests that the till may be as thick as up to 60 meters thick. That's that groundwater dam, like I mentioned earlier. So you can start to pick out where all the glacial deposits are. Coming a bit further towards the southwest, you can identify and model the thickness of some of the gravel deposits. And you can see this whole staircase. You've got the Setwell gravel, Western Green, Chorley Wood, Beaconsfield gravel, Gerrard's Cross, Winter Hill gravel. Again, you can start to pick up a picture of various gravel deposits. And then you can also start to look at more regional, the more regional picture, looking at across the whole of the Chilterns. We can start to do bedrock, larger scale bedrock models for the whole region, using the various different formations at a sort of much more regional scale model, and see how the geology changes. And what this does demonstrate is that, particularly in the north east of the area, once you get past the Anglian glacial limit, is that there's actually a very complicated quaternary story that has been identified from work by Phil Gibbard and many others over the last sort of 20, 30 years, from working in gravel pits. But of course, it's that's only a part of the story. So when you just look at the gravel pits, you get nice sections, but that only gives you pinpoints and snapshots. It's often by looking at the areas in between that you actually get the full story. So we can identify, for example, where we've got the terraces go across, and then you've got an Anglian ice sheet, and then you get a lobe of ice coming down, cutting a buried channel, and then you get outwash gravels coming in, deposit gravel, then you get another glacial advance coming in, then another till, and then more outwash gravel. So it's actually really quite a complicated story. So it's so the mapping has helped to understand that and how that impacts then on the groundwater flow. So just to finally sum up where we are with the mapping at the moment. So we're currently working with Chilterns, but there's still a lot to do. So this we've done over the last number of years. We've done a lot of work in southern England, mapping the whole of southern England, the Hampshire Basin, South Downs, most of the Berkshire Downs, for example, bits of the North Kent, the North Downs. Currently working with Chilterns. We've done some work up in East Anglia. We're also currently working in the Yorkshire Wolds with Yorkshire Water and the EA up there. So we've covered pretty much the whole area from Flamborough Head down to the Humber. That's a whole other talk there is, by the way, because what we've demonstrated there is that the faults that you can see on Flamborough Head cut through the whole of the Yorkshire Wolds, the northern part of the Yorkshire Wolds, and have a big impact on groundwater flow. So there's an awful lot more faulting up there than was previously recognised. It's interesting there actually because that's a classic cases where there's a lot of work done looking at the deep seismic structure for oil and gas exploration, and they identified all these faults in the Jurassic at depth, and then they all stopped at the base of the Cretaceous because everyone thought, yeah, the faults don't go to the surface; they will just stop by the chalk was this uniform blanket. As it turned out, from the mapping we've done, all those faults do actually continue to the surface, and the chalk is actually heavily faulted, and in some places unstepped as well. So, yeah, maybe that's another talk. So, as I mentioned, we're currently working in the Ribash Stork area up here with Michael Kahinde in the EA team there. We're working in the Henley area thanks to Nigel Hode, and we're looking also to carry on the work into East Anglia, but also do some more work in the North Downs. So, there's still plenty of work to do. So I think I shall leave it there and happy to answer any questions.